Good evening, everyone. Welcome back to the University of Washington and to this continuing series on the underlying science behind the proposed methanol plant. I guess it's still a proposed plant. My name is Joel Baker. I'm professor of environmental science here at UW Tacoma and the science director for the Center for Urban Waters. And welcome all of you to our campus. Today's session was organized around the theme of potential environmental impacts of the proposed facility on the local and regional and indeed global environment. Somebody asked me, actually more than one person asked me, are you going to continue this series even though the proposal was put on hold? And the answer clearly is yes, you're all here and we're here. But I just wanted to comment that we're going to continue these types of series well into the future. Although this is an issue that is front and center in the community, I think the best time to learn and to think is not when you're in the moment of a crisis or of a really heated argument, but under a more relaxed time. So look forward to a continued series of discussions, not just about this specific proposal, but other environmental, other water-related issues in the Tacoma area. So stay tuned for that as we go forward. So without further ado, I want to introduce our panel. We have three excellent speakers tonight. Sheri Tonn is a professor of chemistry at Pacific Lutheran University. There's two small schools in Tacoma, and I always confuse them, so sorry. And then you get beat up. Pacific Lutheran University. Sheri is one of the founding directors of Citizens for a Healthy Bay, which you all know about. Also, I found out one of the founding directors of People for Puget Sound, which is a long-serving environmental nonprofit in Seattle. Ed Kolodziej is an associate professor of environmental science here at the University of Washington, Tacoma. He has degrees in chemical engineering from Johns Hopkins University and his Ph.D. in civil engineering, civil and environmental engineering from Berkeley. Not Stanford, but Berkeley, which I also get confused. And then finally, Joe Casola is the associate director of the Climate Impacts Group at the University of Washington. Joe holds degrees from Duke University, which I discovered, so he's a Dookie. Slipped through the cracks. More importantly, he's a Husky. He has master's and Ph.D. in atmospheric sciences from the University of Washington. Has been actively engaged in climate issues for a number of years. So we're going to start off with Sheri, and then Ed, and then Joe. Same format as before. Each will give about a 15-minute presentation. We'll take a short break, and then we'll do Q&A. So turn it over to Sheri.
Great. Well, as we all know, this site was originally a Kaiser aluminum plant site, which I plan to talk about this evening for a little bit. And because of being redeveloped, it's being redeveloped under the auspices of being a brownfield site. We have another brownfield site in Tacoma, and that would be the Assoc smelter site. The Assoc smelter site, of course, was cleaned up with a lot of contained materials on site and has been redeveloped into mixed use and housing. By comparison, the brownfield site for the Kaiser aluminum plant is indeed being redeveloped in terms of being an industrial site rather than being developed to clean up standards for housing or mixed use. As we look at this site, it could be Northwest Innovations that actually would be the long-term tenant on the site, or it could be somebody else, but it would likely be industrial. If we think back to the development of the port has a long industrial history. The Assoc smelter was originally founded in 1888. The tall stack was, first of all, Guggenheim spotted and it became Assoc in 1905. The tall stack was built in 1917 at Assoc. The Port of Tacoma was created by a vote of the residents of Tacoma, by the residents of Pierce County, actually, in 1918. In both World War I and World War II, there were extensive shipyard developments in Tacoma. Hooker Chemical Company, later to become Occidental, was founded in 1928. The first paper plant came to town in 1930, and smelting came to town for aluminum at the time of World War II. And of course, aluminum was a strategic metal for World War II. It became Kaiser Aluminum in 1947 after it had been closed for a couple of years, and Kaiser first leased it and then purchased the plant. Another facility in Tacoma that was part of the industrialization was U.S. Oil and Refining in 1952. There are a ton more industrial facilities in Tacoma, but this just gives you a highlight of some of the developments that had happened up to the time of about when Kaiser came to town. In 1968, a tall stack was installed at the Kaiser facility. And the tall stack was installed because you can see quite a bit of smoke here. And there were indeed emissions of both fluoride and carbon in the form of soot from that facility. The tall stack was 500 feet tall. The Assoc stack, by comparison, was 565 feet tall. So this was one very tall stack. Just like the Assoc smelter, it distributed materials over a fairly broad area, but fortunately, most of these materials were not as toxic or have remained around as long as the results of the Assoc stack distributing arsenic through the Rignon. So the smelter actually got its raw material from Australia, and it got its raw material in the form of alumina, which was processed bauxite ore. And of course, the reason it came to Tacoma was because of cheap power. The power in the Northwest is what brought a lot of aluminum smelters here to the Northwest, and that power remained cheap right up through when the smelter closed. They had a long-term contract for cheap power. In 1998, the smelter employees went on strike. And the employees were on strike for a while, and then there was ultimately a lockout at the plant. And Kaiser locked the employees out, and eventually in 2000, the smelter closed. Now, that smelter actually smelted alumina through the process of electrolysis. So it used electricity to smelt the alumina into molten, into molten aluminum, and it used a material called cryolite. Why this is important is because there were carbon liners that acted as the cathode. The iron vessel was lined with carbon, and then there were carbon anodes. So on site, there is still to this day a lot of waste carbon. Much of it was removed by Kaiser, but there is still material on site buried from the processes that went on here. Here's just a picture of that aluminum being poured, and these are actually, this is an example from inside the smelter of the pot lines. So you'll hear these referred to as pot liners because they lined the pots that were actually used to smelt the aluminum. So historically, there was a lot of contamination on site, and that contamination included spent pot liners, and those contained carbon, fluoride salts, which was involved in the processing. That was part of the that was one of the components in cryolite. So a lot of fluoride salts. Cyanide is a byproduct of the reaction process for making the aluminum, and a lot of polyaromatic hydrocarbons. There was also spilled PCBs on site, although most of those PCBs have long since been cleaned up. There are a variety of kinds of metals on site historically, as well as spilled diesel and other petroleum hydrocarbons. So historically, there was a lot of contamination on site. Part of that contamination was cleaned up by Kaiser during operations because, of course, agencies noticed what was going on there. And part of it was cleaned up, has been cleaned up later on. I mentioned the smelter closure happening in the year 2000 because of the labor disputes. In 2002, Kaiser declared Chapter 11 bankruptcy. And after it declared Chapter 11 bankruptcy, the port purchased the site. We know it's 98 acres, and there aren't very many sites within the Port of Tacoma that are that large. So the port viewed it as a good investment, particularly since the site was sitting there as an abandoned industrial facility with no known use going forward. When the port purchased the site, they made certain commitments to the Department of Ecology, and that included redevelopment of the site for port purposes, proper management of the waste, performance of specified cleanup actions under an order or a consent decree. And we're going to come back to that. So when they purchased the site, the appraisal was $27 million. The agreement with Kaiser was they'd get about $12 million. About $4 million would be put in escrow for cleanup of the site, and there was an allowance of about $10 million for demolition. So that adds up to the $27 million, which matches the appraisal. Ultimately, there was some money recovered from Kaiser, so the net paid to Kaiser at that point in time was about $14 million. So that's that $14 million. To date, roughly $14 million has been spent on environmental cleanup and demolition of the facility. There have been some credits back from Kaiser. There was a MOTCA grant for $2.4 million approximately, and there's a long-term monitoring costs of about $1 million in the budget. So that means the total costs to date are about $23.5 million to get us to this point. If we take a look at the site in 2002, you can see that there were a lot of buildings on site. And there are about 75 buildings on site in total. And we're going to come back to this figure later on. So remember kind of this geometry. In 2006, the stack was demolished. And when the stack was demolished, they needed to clean it out because the stack actually included about 1.5 inch thick soot inside. And that soot added up to about 100 tons of soot that was removed before the stack was demolished. And that was July 2nd, 2006. And that was part of the overall demolition of the smelter. Okay, so this is that same aerial view of the site in 2010. And you can see that most of the facilities had been demolished. There's a few little buildings down there that remained. But essentially, materials had been removed from the site, so the site was relatively clean with regard to the surface. The amount of material taken off the site was in millions of tons. A fair amount was recovered and recycled, and somewhere around 75,000 tons of steel, copper, aluminum, alumina, and other metals were recycled, and cement were recycled from the site. And several million pounds of material also went to either contained landfills or to regular landfills or were spread on site. Various holes on site were filled up with dredge materials from the Blair Waterway, so the site was essentially leveled and had a fill of anywhere from, 2 feet to 18 feet of materials to make the site level. So that's largely where the site is today, except that there have been some more cleanups take place. The areas of significance that ecology and the port identified were the log yard area, which had some Asarco slag, the wet scrubber sludge area, which is a contained landfill area on site, which has stuff in it and probably has the highest concentration of remaining carbon, PAHs, and cyanide. The rectifier yard area, which is the area where the PCBs were spilled and cleaned up, and they have been cleaned up. And then a couple of remaining areas that needed cleanup in 2012, the spent potliner area and the rod mill landfill area. So through an agreement with Department of Ecology, while they were working on the final plans for cleanup for this site, they developed an interim action plan. First I ought to say there have been a lot of agencies involved, Ecology being lead on this site under MOTCA, the Model Toxics Control Act, with responsibilities from RCRA, the Federal Resource Conservation Recovery Act that deals with hazardous materials. So Ecology's been the lead. EPA has been involved from the point of view of RCRA, but Ecology taking the lead, and then of course other entities involved as need be. So the remedial investigation was published in 2012, and it identified the extent and nature of contamination for those 6 targeted areas I just showed on that map. The spent pot lining area, the rod mill area, closed landfill, the rod mill former demiser oil area, rod mill former stormwater ditch, former rectifier yard, and the former log yard. The 2 that are in red are the 2 where interim actions have taken place since 2012 to clean them up. And for the most part, that land has been excavated and hauled off and capped with clean materials. So where are we today? Well, 2012 was when the remedial investigation feasibility study was done, and 2016, this spring, we're hoping to see a consent decree and public action plan available for public comment. And those documents are apparently close to done and should be released by the Department of Ecology. So that's going to be something really important for us to keep an eye out for. The cleanup action plan, in this case, cleans this site to industrial standards. So that's different from the cleanup that's gone on at Point Ruston. So with industrial standards, it means that this property needs to be continued to be used for industrial uses. Because the plan is to reuse it, because the port has paid $24 million for this site, they've also included a materials management plan in the cleanup action plan. And that means that when somebody does come up with a plan to reuse it, they have to follow this plan to be able to redevelop the site. And if they're digging in the dirt, doing anything significant in terms of excavation, they need to be actually either following the plan or preparing a more extensive plan for Department of Ecology. So this doesn't matter if it's Northwest Innovations or if they go away and some other developer for the site appears, that entity would follow the same kind of process here. Before Northwest Innovations, there was actually another potential leasee for that property, and they too would have followed that material management plan. These documents are legally enforceable by the Department of Ecology, and after the consent decree becomes final, environmental covenants will be filed on this property. So that's where we are in terms of the site. It still has contamination on the property. In addition to having contamination, it has monitoring wells on the property, and those monitoring wells will continue on forever. In addition, the cleanup action plan will specify if there is additional cleanup to take place on this property. So for more information, watch Citizens for Healthy Bay website and announcement, and be checking the Department of Ecology Port of Tacoma Kaiser website for those documents. If you really like reading documents, you can read the interim cleanup plans on the Department of Ecology website. And at only 300 pages each, it won't take you long to get through them. Thank you.
Thank you, Sheri. So we're going to turn over now to Ed Kolodziej, who's taken the courageous act of trying to estimate emissions from something that doesn't yet exist. So, Ed.
The typical protocol when you start a talk is you say thank you for the opportunity to give a talk here. And this is one of the very few where I have really mixed and ambivalent feelings about standing in front of an audience giving a talk on something where the debate is heated, because that's a little bit like saying thank you for the opportunity to come like beat me on the head with a stick. Anyways, so why am I up here? Well, pretty much I have a background in chemical engineering and environmental engineering. And really what I do for work is think about chemicals going out in the environment, especially ones that end up in water, and try and figure out where they go and like how much we should worry about them. So that's really the perspective I think I bring to the discussion today. Although like Joel said, we don't really have a lot of specific information, so I don't think I can accurately estimate some of these like specific quantities going out in the environment. So, in general, as a scientist, right, I need some data if I'm going to try and make a prediction or figure out and analyze a system. And really, I think the biggest challenge I ran into when trying to think about the methanol plant here in Tacoma is the fact that we do lack a lot of technical data and facts. So we're really operating in a bit of an information vacuum, which means predicting risk and impact is pretty tough. So I think the best I can do today is think about general trends and issues, no real specifics. Unknowns definitely exist. I'm not pretending to give a comprehensive analysis here. There might be some things I haven't thought of or things that haven't come up. And I'm basically coming at this, issue assuming that this plant is a well-designed process, so it's well-engineered, it's well-managed by a responsible company. And we know from the history of industries in Tacoma and elsewhere that hasn't always been true, but I pretty much figure I'm starting from the point that everybody does their job and does as good a job as they can. So that's that. So as a chemical engineer, when I first heard about a methanol plant in Tacoma, I didn't really blink at that. To me, a methanol plant where they're making methanol from methane involves simple chemicals in a simple process. And usually when you think about simple chemicals out in the environment, that's generally a better thing than more complex chemicals out in the environment. And granted, there's always distinctions there, but my little alarm bell radar detector did not go off when I first heard this. So that was maybe the first thing. It's combining methane, which is over here. I always like molecules, so I put a few up here. So carbon in the middle plus 4 hydrogens. That's roughly as simple as a molecule you can get. You combine that with oxygen, the 2 red O's here, another very simple molecule. There's a catalyst in there with some nickel, copper, and zinc, so you get a little bit of metals in here. Those are less simple and maybe more to think about. Water is involved, so water is a byproduct here. And you're making methanol over here, CH3OH. So again, simple chemicals in this process. And I think when you think about simple chemicals go out in the environment, that's generally a good thing. Microbes know how to handle simple chemicals. Oftentimes, simple chemicals have relatively lesser risks, especially for things like carcinogens, being a carcinogen or things like that. And I think the key chemicals to think about here are obviously the methanol. We've heard lots about methanol. When it comes to environmental discharges, we have to think a little bit about these metals. Sometimes those have some impacts if you put a lot of metal into the water. And then methanol is a product here, but there's also going to be some impurities. And I think this is the place where I think unknowns might live the most, or there's just no available data as far as I can tell to see what impurities we have in the system here. Of course, in reality, the process isn't as simple as I just pictured. I think this was the one they had up on the Northwest Innovation Works website. One of their contractors had this process. The reality is it probably looks more like this, like chemies would be more familiar with something like this. And that simple process occurs in a bunch of steps. All these unit operations are doing something. And so I took a look at the system like this and tried to think, well, what's coming out of these boilers? And what might be happening over here to result in some pollution of wastewater that you end up sending off to the wastewater treatment plant or something like that. So a key thing for us to kind of figure out the potential impacts here is what can we compare this process to? And as far as we can tell, the only real comparison that's based on a very similar identical process is this Coogee methanol plant, which is located near Melbourne in Australia. And one thing to note is that that's a really small plant. It's a pilot scale plant, which means it makes 80,000 tons per year. if the Tacoma plant came up to full scale, it would be making 80,000 tons in 4 days. So there's a drastic difference in size. And I think one of the take-home messages from my slides here is that the Tacoma plant is very, very big. And so that's really a take-home message that in some ways drives some of the potential environmental implications and chemical releases. The Kolodziej plant doesn't have too much recent data, and it's reasonably comprehensive, but it lacks certain process details. So I don't have all the information to make a really good analysis. So I think I know a little bit, or we know a little bit about what chemicals might be emitted from this, but not their concentrations. And one thing you hear in toxicology is the dose makes the poison, right? So it's going to be pretty tough for us to figure out anything in terms of concentrations that are coming out at this point with the data we have. Air emissions. So I started thinking about what might this put into air. And you can first start with the natural gas pipeline. Again, this is kind of a process flow diagram. This is from the Northwest Innovation Works website. I think this is their scoping documents. We might have some leaks of methane here. And I decided I wasn't really going to focus on those. I think Joe Casola from the Climate Impacts Group has a lot more insight into methane leaks. So I basically ignored those in my analysis. Air emissions. So I think one of the places to really consider what sort of air emissions we might expect from this plant is understanding how much of that natural gas or methane goes toward heating the process up or being burnt or oxidized to create this synthesis gas here. So there's basically a suite of air pollutants that look like combustion-derived pollutants. This is things like carbon dioxide, carbon monoxide, nitrous oxides, sulfur dioxide, volatile organic chemicals, which are typically small hydrocarbons. They might basically be impurities or byproducts from a combustion process. Unburnt fuel is an example of something that would end up as a VOC. And then you would have particulate matter, which is like the soot that Sheri talked about being in that old smokestack. That's particulate matter. So this suite of combustion-derived products are really the same types of products you'd expect to see from any type of combustion process. If you're burning natural gas in your grill outside, or this is relatively similar to what comes out of the tailpipe of a car, or a natural gas plant that makes electricity, or anything that's just burning natural gas for heating purposes. I found, it was very difficult for me to tell of all the methane coming in, how much of it was going to go toward heating the process versus ending up in the methanol itself. So that's kind of an uncertainty. When you move beyond those combustion-derived pollutants, there's another set of pollutants that really come from the process, which is really you've created a synthesis gas from the methane, and then you basically react that over the catalyst to make the methanol product. So these are the steps where the methanol product is created and then distilled to get its purity up higher. So there's a suite of process-derived pollutants, and the big difference in those process-derived pollutants are you might have a little bit of residual methane that hasn't been oxidized or combusted. Now you've started to create chemicals that look like methanol itself, organic impurities that are things like ethanol and other simple organics. And so I think you'd have a suite of simple hydrocarbons and VOCs coming out of this process type step. And when you look at the discharge data from the Kolodziej plant in Australia, they talk about VOC emissions, but they don't really break down what their chemical composition and their cause are. So we know there's a suite of process-derived pollutants that come out of the step here, but again, it's really difficult to tell exactly which ones are there and how much. So those right now are definitely unknowns based on the data that we currently have. So one thing I really came to appreciate a little more as I looked into this is I think the venting and fugitive emissions that happen when you're filling tanks this is one of these things where as I learned more, I kind of began to respect a little bit more the potential for venting especially to result in maybe moderate to substantial concentrations of methanol in the air at this facility. Right here, this is a picture of the Kolodziej plant in Australia. This is a pretty small plant. Obviously, the Tacoma plant would be far larger than this. But you can even see in the photo that's online, they have a tanker loadout vent. There's also going to be venting for the methanol storage tanks. So if this tank was empty, like for example, you just pump this tank into a tanker ship in the Tacoma harbor, and you're producing methanol in your process here, and you have to fill this tank, this has air or nitrogen or something in it when it's empty. And as you fill it, that air needs to go somewhere, right? And because methanol is very volatile, it boils at a relatively low concentration. Anytime you're handling or moving methanol around the facility, you're going to have venting emissions. And from what I could tell looking at some of the existing methanol plants, it's not actually the process itself that always creates the bulk of the air emissions from the facility. Sometimes it's just the venting process here. So I think I would really keep an eye on the venting and fugitive emissions. Most venting systems do have scrubbers and things like that to reduce methanol going and anything else going up into the air, but they never work perfectly. There's always still some coming out. So I really started to think that maybe the venting emissions might be more important than the process emissions, at least when it comes to air emissions. Same thing when you fill a tanker. For example, they're putting this potentially in Tacoma because Tacoma has a port and you can make methanol and fill really big ships. Again, you have a ship that arrives in Tacoma empty, like this one is, there's the water line, and you're gonna fill this with methanol. All those empty tanks are gonna start to vent as they're filling them because again, that methanol is pretty volatile. So I'd keep an eye on venting emissions from the loading process too. And again, these ships have scrubbers. They pull the methanol out of the air as the tank vents, but I don't have a good feel as to exactly how much those scrubbers will remove. So I think that's something to keep your eye on there. So that's the air emissions. What about the water? Again, we have a little cartoon type diagram of the process here. I couldn't find any information on emissions from any type of water pretreatment, right? It's often the case that an industrial process needs to pretreat the water to get it to a high enough quality to put it into the system. We really don't yet have any indication on what emissions might come from pretreatment. The same thing with the natural gas has a desulfurization process which scrubs sulfur out of the process in here. I don't really have a good feel as to whether that has any aqueous emissions at all, or is that all air emissions or solid emissions from kind of as solid phases. Cooling towers, most of the water going into this plant is used for cooling the process. This is the process that runs at high temperature, basically. I think I saw 700 and 1,000 degrees Celsius, so there's a lot of cooling. Cooling water isn't really going to be a problem for emissions in the aqueous phase. You don't typically have direct contact between your cooling water and your process, so this is just water running over the outside of a heat exchanger and evaporating and going up into the air as steam. So I didn't really pay too much attention about water emissions there. I'm not so worried about that. And then finally we have the wastewater treatment. 1.4 mgd, so about 10% of the total water going into the plant is expected to end up as a wastewater effluent stream that is essentially going to be discharged to Tacoma's wastewater treatment plant. That 1.4 mgd is less than 1% of Tacoma's wastewater treatment plant capacity, so there's plenty of capacity at the plant. The pollutants, as far as I can tell, that would be in there would be methanol, ethanol, maybe some trace metals from the catalyst, but the catalyst doesn't really dissolve and disappear, so if anything, I think trace metals would be pretty low, but you still have water flowing in stainless steel pipes and things like that. It'll pick up a little metal along the way. Some hydrocarbons, again, these weren't really defined in the Kolodziej information, and then maybe you have some dissolved solids or salts that essentially are byproducts of the evaporation process. So evaporation doesn't pull the salts up into the air. You have a high salt concentration, product water left behind, and that would end up in the wastewater as well as some heat. So at least some of this wastewater is wastewater that comes from the cooling towers, and it's warmer than typical. So you might have to consider a little bit of heat ending up, or warm water heading over to the wastewater treatment plant as well. This is the Kolodziej wastewater emissions little schematic they had. Again, not a lot of detail there, but if you look at it, they're really focusing on the discharge specifications for their municipal wastewater, which ends up in the sewer system and onto the wastewater treatment plant as methanol and ethanol. So that seemed to be the biggest organic pollutant coming out of this methanol process. So everything I did there was routine operations. What happens to methanol fate in the environment? Here's a little table I pulled from the EPA here. You put methanol into soil, it lasts 1 to 7 days. Air, 3 to 30 days. Surface water 1 to 7, groundwater 1 to 7. So methanol is a pretty simple molecule, and it degrades pretty rapidly. It's generally biodegraded by microbes. So it's short-lived, days and weeks. I would say no matter what happens at the Tacoma facility, if it's built, you're not going to worry about methanol being a long-lived pollutant which is present months and years after any kind of event. Methanol goes out in the environment and basically disappears pretty quickly. It's biologically degraded by microbes. You can see that here. This is a plot that has the percent of methanol remaining. Notice this is a log scale where you have 100%, 10%, 1%, and time in days. So this is about a month here. So if you put methanol into a surface water, that's this data figure right here, you're basically losing a log unit every 10 days or so. So 2-3 weeks later, you have 1% left. By the time you get to a month, you have, a fraction of a percent of methanol left. So it doesn't last a long time in the water. That tells us we worry more about acute effects versus chronic effects. If methanol gets out into water, you worry about everything on a short-lived time period, very quick, sudden shock to the system type event. So what happens to methanol in water? The main thing that happens is if you put methanol in water, it consumes oxygen. Methanol going into water is converted to CO2 and water molecules itself, and that's consuming oxygen along the way. So if you suddenly spill methanol into water, water typically contains about 5 to 12 milligrams per liter of oxygen. You add methanol to water and the oxygen is going to be depleted. So that's what's shown here. Boom, you get a drop in oxygen with time in the water. And the reason that matters is because if you do have any kind of methanol spill event or methanol getting into surface waters, it's going to be an issue for aquatic organisms that require oxygen. Fish need oxygen to breathe, and methanol is an organic, it's an organic compound that's an oxygen, it exerts an oxygen demand on water. So I think most of the issues with respect to adverse impacts of methanol would be if you ever had an event that put a lot of methanol into the water. You'd expect it to kill a whole bunch of fish. So when I was here in the first talk here, I drove home and I was thinking to myself, what would be the worst case scenario that I could think of? If, how could we get a whole bunch of methanol in water? How bad would that be? Would that be something that you were really concerned about? So I thought to myself, well, a worst case analysis would be if we lost a tanker of methanol into Puget Sound. That's basically the worst thing I could think of happening with respect to the methanol facility. This would be a low probability event. This should ideally never happen, but I think it's important to consider what might happen if it did. If you do the calculations, you put a week's worth of production, 140,000 tons of methanol into a tanker. Puget Sound is about 6 milligrams per liter of oxygen. Every gallon of methanol spilled into water requires 198,000 gallons of water to satisfy its oxygen demand. So a tanker event would be pretty significant. If you did lose a whole tanker in the Sound, you would need the oxygen from many, many gallons of water to basically degrade the methanol and convert it to CO2 and H2O. If you roughly figure out what volume that is, that would be exerting oxygen demand on roughly this amount of water in the Sound. Something up on the top of Vashon Island down to Commencement Bay. The reality, would be the Exxon Valdez case, right? The reality is a bunch of this methanol would volatilize. You probably wouldn't lose all the tankers, so it'd be less, but this would be what the worst case looks like in terms of the bay. So when I drove home, I figured that if you compared a methanol tanker spill to an oil tanker spill, it's terrible in either case. These should never happen. The methanol tanker spill, you'd have a bad first month with lots of dead fish, but the methanol would deplete and you wouldn't really have a lot of long-term pollution. When it comes to an oil tanker spill, by comparison, that's something humans are pretty familiar with. We know more about that. That's a long, slow catastrophe with years and decades of residual pollution. If you had to pick, and again, it's a terrible decision in either case, you'd pick the methanol tanker because it'd be really bad for a month, and then you'd be kind of okay. Well, in relative terms. So what else happens to methanol? One thing I was focusing on a little bit is methanol actually acts as a co-solvent for organic contaminants. And I think this is important to think about. Sheri mentioned the fact that the site is a brownfield, right? And so there are contaminants present on site. And if you put methanol into water, it actually acts like a detergent, and it moves contaminants from contaminants that would typically be stuck to soils. So what you see here is 0% methanol in water. Most of this TCE is stuck to the soil. As you start to increase the amount of methanol in water, more and more compound gets dissolved because the methanol is acting like a detergent. So I think that would definitely be an issue for the site. Any site that had PAHs or PCBs, if there were any sort of on-site spills, you might start to move some of these chemicals off-site. And I think that's true for both organic and metal pollutants. So that would be, you'd have a little bit of a risk of creating larger groundwater pollutant plumes or moving increased transport risk of methanol, of contaminants that already exist on the site. It'd be easier for them to move around in the water. So a rough summary of the chemical risks. If we're thinking about just the risks of chemicals coming off the methanol plant, and where should we focus on the details? My take-home message from from doing this analysis was, I think we should, for routine operations, it's important to think about what fraction of natural gas is combusted for heating and electricity, because that's really going to drive those air emissions of the combustion products. We don't really have a good idea of what fraction of the natural gas actually ends up as combustion products. I think we should pay attention to venting emissions of methanol during materials handling. There's really no information about emissions from the desulfurization or catalyst metals, so that's a big black box right now, and as well as specific chemicals in the processed wastewater and what exactly those impurities were. So those were the uncertainties I really ran into as I thought about this process. In terms of accidents, personally, I think I'd be more worried about an accident possibility than routine operations. Just the physical size of this plant is a really big risk factor. This is a very large facility, therefore the potential for very large accidents does exist. These accidents should be rare, but big accidents could be extremely consequential. And then I worry a little bit about the fact that on-site spills on a brownfield do increase the pollutant transport potential. I was hesitant to even put this up here. But I basically said to myself, okay, if we have a gradient of good to bad, so if this site had a rainbow and we were planting flowers there, I really wanted to find a picture with maybe like a unicorn here. This is like the perfect, most ideal industrial site you could think of in Tacoma. And I created a gradient from pretty good to terrible, where terrible might be things like the Assoc smelter that used to be in Tacoma, or the Kaiser facility, or 1950s, Soviet bloc industrial production, maybe modern day industrial production in like China, right? If that was really terrible. I felt, and again, my opinion, based just on the chemistry, the chemicals here, I would kind of land this guy somewhere in the middle. And recognize there's big error bars here, right? If you did something like a pollution offset where you used the construction costs of the methanol plant to maybe reduce emissions elsewhere in the port, this might be near neutral. It's big, though, so maybe that's just bad. It might put a pretty big mass of pollutants up into the atmosphere just because it's really big. Even though at any one moment it's relatively clean, it's still a very big facility. But then again, if a bad accident happened, this could easily get to terrible for some of those things like a tanker accident. So I didn't really think it was environmental Armageddon, largely because we're dealing with simple chemicals here that actually have a relatively limited suite of health risks. It's not nearly the biggest polluter among local and regional industries in perspective, but it does have real risks of accidents and spills, especially because it's quite a big facility. It would help to have more data to accurately prioritize chemical risks from us, but I think that data alone isn't going to help us make hard decisions about values. And I think that's where a lot of the challenge of thinking about a methanol plant in Tacoma comes from. It comes down to what values we have about certain things in relative terms. Yeah, and that's pretty much it. So a few references here.
Before we move on to Joe, that we are taking questions from you all. If you have questions, there's cards available. So pass them. We're going to do the same thing we did last week. Melissa Malott from CHB will moderate the Q&A session. So I'm sure there's lots of good questions that have been generated already. I have a few. So please do that. So next, we're going to get into the issue of climate change, which is both impacted by the plant and impacts the plant and vice versa. Very complicated thing. So we're really fortunate to have Joe here from the Climate Impacts Group. I can say this was not part of it, it's the leading group in the country, if not the world, on assessing the impact of climate change on us. So, Joe, welcome.
Thank you.
Over there,
Okay. Well, everyone's very polite when Joel said I went to Duke. Most of the time, that's either a lot of booing or people just leave. So thanks for tolerating me. Yeah. So I'm from the Climate Impacts Group. We're a research group at the University of Washington. And we've been around for, up in Seattle, we've been around for about 20 years. And what we do is research on climate variability, so kind of things like El Niños versus La Niñas, as well as climate change. And we try to connect that research to the resources in the Pacific Northwest, our water, forests, fish, infrastructure. And we really try to interact with those that manage those resources, both as a way to inform their decisions, but also to feedback and drive the science that we're doing. So we have lots and lots of reports, so if you're really interested in any kind of climate impacts in the region, please do check us out. Okay, so in my talk, I'm going to take up two questions that Joel mentioned. One, how does climate change impact the plant? And then how does the plant influence climate change? Essentially, what are the plant's emissions, and can we put them into a broader context? And before I take these two questions up directly, I think a good starting point is to say, well, what are the impacts that we expect in the region? That can both inform what will happen in Tacoma and in the port area, but it can also be part of why we care about emissions. And in November, we produced this report here. It's an assessment of climate impacts in the Puget Sound with significant contribution and support from Joel at the Puget Sound Institute, and continuing as we talk to people about what's in here. So if that is of interest, this is a nice kind of one-stop shop to get started. And a lot of the figures I'm going to show are actually in that report. Okay, so what do we expect to happen in the Puget Sound region? Well, the first one, which is I think an obvious one with climate change, is we expect the future to be warmer. We've had warming in the 20th century. This graph shows from 1950 to 2100. The black, and it's a little faded out here, is gray. The black is an average of a lot of models. The gray are individual models. And you can see there's been warming, and then there's a lot more warming heading our way. And the two curves here, the red is kind of more of a business as usual for global emissions. And we could have warming on the order of maybe 10 degrees Fahrenheit in a given year. And to put that in perspective, by the end of the century, if the globe starts to reduce emissions pretty significantly, we might keep that warming more in the 5 to 6 degree Fahrenheit range. And to put this in perspective, last year, 2015, which was the warmest year for the planet and the warmest year for Washington State, last year was around 4 degrees warmer than this average number. So that's like saying by the middle of the century, last year's very warm temperatures would be average. And unfortunately, I forgot to put my numbers in here, but mid-century warming, you can see 2050 is kind of the 4 to 6 degree-ish range, and then end of century could get much larger, but really depends on emissions. Another important impact for those of us in the Sound is sea level rise. We've observed over 8 inches of sea level rise in the 20th century. There's a huge range for what might happen going forward. And some of that is uncertainty in how much warming might occur, and some of it is what is warming's impact on ice sitting in Greenland and Antarctica. So you could have numbers as much as 5 feet. It could be very small. It could be something kind of on the order of several inches. This is also affected locally by what the land surface is doing. In some parts of the Puget Sound, like Neah Bay, for example, there's so much uplift that it's essentially offset all the warming, the sea level rise that's happened in the 20th century. Other parts of the Puget Sound are sinking. South, the farthest in general, rule of thumb, the farther south you go in the Sound, the more sinking you see, but usually only adding a couple inches to these numbers. It's not kind of dominating. But I wouldn't expect in Tacoma uplift to save us the same way it may in other parts of the sound, or to offset. Another big change is how our hydrology changes. And this is really, to a large extent, temperature driven. So this curve shows, it's for the Puyallup watershed, and it's actually a spot in, on the White River that this gauge is, or a simulation of this gauge would be. The black is the stream flow you get in a month historically. So you see, and this graph runs from October to September, so the water year, starting October 1st and then ending the following September. And so you see an increase in stream flow, kind of a bump here in the fall. We get a lot of rain in the fall. And then it decreases because a lot of the watershed is actually high elevation. It's cold. It gets snow. So a lot of that doesn't run off, and it gets collected as snow. And then as you move into the spring, the snow shifts back to rain, and some of that snow starts to melt. And you get the really big peak driven by snowmelt in the summer, usually June, and then you kind of ride that snow out to the end of the water year and then wait for the next year. So that's the normal, what we're used to. And this is really common in watersheds across the Puget Sound where you have rain and snow contributing. As we go in the future, these different colored curves are for different dates in the future. So the blue is kind of next decade-ish. The mid-century is yellow, end of century is red. And what you see is that summer peak starts to go away and the fall peak gets bigger. And this is really the shift from snow to rain. As we warm up, we get more and more of that precipitation falling as rain, and it's running directly off. It's not being stored up in the higher elevations. So this kind of shape where you get this big peak and not much else, that's a rain-dominated watershed. So we're shifting from a watershed that has snow and rain together to one that's almost all rain. And I need to note that this is for unregulated flows. We have dams, right? And dams act to smooth this out. So this is not what you would see if you stuck a stream gauge just in the channel because we have dams that operate. But the dams are optimized for that black line, and we're really doing a lot of changes. I should also note that this is for the river that's nearby, but the water system, Tacoma Water, actually pulls from the green a little farther north. But the green has a similar kind of elevation profile with it, so it still has this kind of two-humped shape, and warming changes it in the same way. So, long story short, we get higher flows during the fall and winter, and lower flows and perhaps longer periods of low flow in the summertime. Heavy rain. When rain does come, we expect it to be more of it. And this is a lot due to just as we get warmer, there's more water vapor in the atmosphere, and if we have more water vapor to work with, it can come out when it does rain. Now, the estimates for how much really span a wide range. It could be just a few % more, for some of these big kind of Pineapple Express events, or it could be maybe a quarter or a third more rain. And this is really an active area of research, trying to understand how these big whopper storms change in the future. With all these hydrologic changes and warming, the ecosystems are going to shift. And we're already seeing some indicators of some climate-driven changes. You are seeing changes in the estuaries, where places that may have been, sea level rise also contributes, may have been more brackish or freshwater. You have more saltwater involved. This is a picture of a harmful algal bloom, that those are likely to become more frequent, and the period of time during the summer when we see them would be extended from warmer temperatures. Obviously fires, big fires, the risk goes up. The last couple of years we've seen some really, some of the worst in state history. And this depicts the ocean acidification, shelled organisms that have difficulty maintaining their shells as there's more carbon dioxide in the atmosphere. That carbon dioxide gets absorbed by the water, and the water's pH drops, and pH, that's a measure of acidity. So as the waters become more acidic, shelled organisms struggle, and those are really important to Washington. So this is just to say that many of the types of species that we care about and the types of ecosystems that we have a lot of environmental rules and regulations to protect, they may be stressed, and that may change the way we make priorities. So, haven't talked about the plant yet, so let's go back to question number 1. That's kind of the quick primer on what impacts might occur. Let's think about the processes at the plant. So first, as we have warmer temperatures, cooling water is a huge input, and Ed kind of showed the high temperatures involved in the process. Well, as you get warmer, the efficiency of cooling goes down. You may need more water at different times of year than kind of if the design is based on past climate. Changes in hydrology may also reduce the availability of that water, especially during the summertime. The changes in hydrology will also alter the electricity supplies if they rely on electricity from the grid. That late summer time is usually when generation is at its lowest. Flooding. The port is obviously an area very prone to flooding even right now. So sea level rise, and it kind of, the increase in flooding risk comes from both sides, essentially from the sound side via sea level rise, and then from the river side with more intense heavy rainfall and higher fall and winter flows. And there's also a sediment component in there too, that as you get higher flows, you can bring more sediment down the rivers. If you have more sediment in the rivers, you're raising the riverbeds, and actually that's kind of what's going on right now in the Puget Sound near Pacific. And then the environmental compliance issue. Warmer temperatures could affect the effluent rules. How warm is that wastewater? How warm can it be? And then other priorities that we deal with as species start to move around, and they are dealing with climate change as well. So that's the one-slide summary of climate impacts on the port and on the potential plant. The important point is that most of these impacts are not just on the plant. They're on the region. The port, the city, the Puget Sound in general. And so the planning for them, it's not just going to be what can we do on this parcel, but I think it's what is going to happen kind of regionally among the resource managers, and can whatever decisions made about the port and its future risk be coordinated with those happening in the region. And fortunately, we live in a region where a lot of the municipalities and the utilities and the infrastructure managers and the ecosystem managers are working on this. So it's not all, I think, a doom and gloom in the sense of preparing for impacts. But I think the one thing to keep in mind that any sort of design assumptions or siting assumptions should not be using past climate as a predictor. Okay, now I'm going to shift over to the second question, which I think is really important for making a decision about the plant. This is a graph that's kind of similar to that temperature graph, but it's not showing temperature. So again, we've got 1950 to 2100. But on the y-axis, we're showing emissions. So this is the global emissions of carbon dioxide per year. And so the black line is where we've been. We're about up to, it's almost 50, this is in gigatons, so billion metric tons. And we have a lot of different pathways we might follow in the future. This gray area, red line, is that business as usual, where the globe kind of doesn't do much about its emissions, and we don't really level off emissions until we get to close to the end of the 21st century. The blue line is if we really got going on everything yesterday, and that we're actually starting to suck carbon out of the atmosphere, globally speaking, by the end of the century. This would be a pretty heavy lift. The interim ones, this kind of bluish line with the orange area, is if we globally peak our emissions around 2050, and the yellow/pinkish area, this is if we peak more close to the end of the century. But you get to pick kind of how much warming you want with these. So, if we get started yesterday, the globe still has about 2 Celsius. Well, it can avoid 2 Celsius of warming, but it's probably somewhere in that 1.5 to 2 range, which it translates to a little under 4. And you can see kind of the other numbers here. These are global numbers, so in the Northwest, our warming would actually be a little bit larger than that. So why do I show this? Well, only to give kind of a sense of scale. I'm going to start global and then work down to the plant. So 50 billion tons of carbon dioxide equivalent, and that means other gases are important, but we can kind of convert them into the common currency of carbon dioxide. The United States is currently accountable for about 15% of that, about roughly a little under 7. China is the biggest emitter now, but we are strongly sitting at number 2. Washington State, if you look at their emissions, it's just under 100 million tons. So we're a little less than 2% of US emissions, and the reason we're kind of low is, one, we're not a super populous state, but most importantly, we use a lot of hydroelectricity. And electricity tends to account for about 1/3 of national emissions. So the challenge of, let's say, trying to jump off this red line and head down to one of these lower emission scenarios is very large, right? We're at 50 billion. If we shut off everything in Washington State tomorrow, no fossil fuels, we would only reduce that by about 100 million tons, 0.2%. It would be invisible on that chart. Not to say, and I don't want to be fatalistic about this, but it's just the size of the changes we're talking about to avoid significant global warming is a big change in the way we use energy. And it's also a big change in deforestation, although a lot of that doesn't happen in the United States. So I just want to frame how large some of these changes would have to be if you think getting to those lower emission pathways is important. Okay, now I'm going to, I thought Ed's caveats were really good, because now I'm going to use all of those. I'm going to do stuff that you're not supposed to do. You're not supposed to mix and match emissions estimates from all sorts of different sources. Those other emissions estimates were all kind of national and global. They're kind of comparable. What I'm going to do next is a little bit funky, just again, because I want to demonstrate scale, not precision. None of the numbers that I've shown are published. They're kind of back of the envelope things, with the exception of I think, some of the numbers for Tacoma where they have a report. But this comparison is not something I would take to the bank, again, for illustrative purposes. And to get better numbers, we'd really need to know a lot about the specific technology and processes involved. Okay, so a way to estimate emissions for the plant is to figure out how much methanol it's going to be producing and some rate. Very kind of simple algebra. And this is really how the EPA does a lot of their inventories as well. If you really wanted to be kind of more holistic in life cycle, you would also look at the natural gas that goes in and how it was extracted and refined and transported, how the methanol got moved around on ships after and maybe by rail or truck, the electricity used, all the energy used for the water, but I'm not going to do that. Again, it becomes a little bit more difficult to do just sitting at your desk. It's a more involved calculation. It doesn't mean you shouldn't do it in an environmental impact setting, but just that there's a lot of assumptions there that I think detract from why we're here. So just thinking about the methanol plant, 20,000 tons per day, and that seems, that's an assumption of full capacity, and that's from Northwest Innovation Works. Multiplied by 365 days a year, you'd get to 7 million tons of methanol a year, which currently the US, or the EPA estimates US production around 2 to 3 million tons. So this, again, echoing Ed, this is a big facility. The emissions rate, I've grabbed these two numbers, one for CO2 and one for methane. This is just a number from this IPCC guidance, an international body. It's a number used by the EPA, but it's from a 2006 kind of handbook that's based on measurements at 4 plants. It could very well be way too high or maybe too low. but it's the number that is available and published. So the rest of the emission numbers really, really depend on the accuracy of this. And I will say, using that same kind of guidebook, coal, the emissions for producing methanol are 8 times higher. So coal as a feedstock is certainly much, much more emissive than natural gas. So if you do that math of 7.3 million tons a year and that 0.67, you get 4.6 million tons of CO2 and then 17,000 tons of methane. If you convert your methane to the common currency of CO2, you have to multiply it by 25 by this global warming potential. So give or take 5 million tons of CO2. So compared to the global stuff, that doesn't really tally. But compared to Washington State's 92 million tons, it shows up. It's not a small source, if that emissions factor that I use is correct. This is our biggest kind of single source, is gasoline for on-road use, or actually transportation is about half of this 92, and then gasoline is about half of that. The city of Tacoma does have an inventory, and some of the port neighbors, there's 4 facilities in the port that actually report their emissions to the EPA. I'm going to zoom in on those. So the city of Tacoma estimates, it's not really a comprehensive inventory, it just looks at energy, transportation, and waste, but it's a third of what you'd get for the plant by itself. And the 4 facilities nearby are around 400,000 tons a year combined. So if that emissions factor is right, this is a lot of CO2, because this is a very big plant, and you produce CO2 when you make methanol. Again, I'm making a lot of assumptions. There could be capture technologies, there could be other steps to the process that reduce this number significantly. But if that emissions factor is right, that's a lot of emissions. Okay, so getting back to the big question, how might the plant contribute to climate change? Globally, the emissions are pretty small relative to the reductions that you need. However, locally, the direct emissions could be a pretty big new source. And here's where everything gets really shaky, because you have to make assumptions not only about a plant that doesn't exist, but all the decisions that might get made if the plant's not here. So the first one is actually just about the plant. Are there, what technologies do they use, or could they design it differently? But if you don't build it here, where else does it go? Does it go to China, where they're potentially going to use coal? Does it go to another part of North America? What does the feedstock look like? What does the process look like? Could methanol be used to displace gasoline? The stated purpose of the plant now is to produce methanol for plastics, but if it was to use to displace gasoline, you'd actually have an emissions benefit, because methanol produces less CO2 than gasoline for transportation uses. If you really care about kind of the big game, can you get reductions elsewhere? For example, it may be expensive to try to reduce CO2 here, but you could trade off somewhere else. Okay, my last slide. Again, I don't want any of this to be definitive, but I think you're pointing out some things to consider and some questions to pursue if the plant is to be taken up more seriously. The climate impacts on the plant, the port, and Tacoma more generally. There's some really, I think, important impacts to consider, and that consideration could affect siting, design, and operations of the plant itself, as well as the utilities in the region. The emissions depend on the technologies and the feedstock, and I think the importance of those emissions do depend on, I think, whether you want to have a local or global view of the climate change issue. If it's just to keep Tacoma's emissions as low as possible, that may give you a different sense of importance than if you want to look more globally and start playing that game of, well, what happens if this plant doesn't go here? And with that, hopefully save enough time for questions.
All right, thank you. I'm sure there's lots of questions. Again, we're going to take about a 5-minute break. We'll reconvene at 7:15. Please send your questions to Melissa. Melissa, wave your hand widely. And we'll get started promptly at 7:15. Thanks.
Thanks, everyone. As we did last time, I'm going to ask questions based on questions that the audience submitted, questions that we've received online, or questions that I came up with while I was listening to the presentations. But the first question I have is, or actually, let me say, I will be asking the audience if you submitted a question, if the answer answers your question, and if it doesn't, feel free to ask a follow-up if I haven't quite gotten the gist of it right. But the first question is for Joel, and the first one is that, and I know you explained this at the first session, rumor has it that the Urban Waters Group is funded by the Port Commission. Is that correct?
No, it's not. So the Center for Urban Waters is owned by the city of Tacoma. It's a partnership. The University of Washington rents space in the building. Puget Sound Partnership, which is a state agency, also rents space in the building. The only financial arrangement we've had is between the University of Washington, Tacoma, and the port. And the port was one of several contributors to an endowment that pays my salary, but we have no direct. I don't work for the port, and no one else at the Center for Urban Waters works for the port.
Thank you. All right, so the first question, and I'm not sure exactly who to direct this to, but I think it might be you, Ed. How many tons of nitrous oxide, CO2, and VOCs will be emitted per year? And specifically, I know you said that you don't have actual data, but when you look at the emissions from the plant in Australia, if the plant here is going to be 91.25 times bigger, which is my math, does that mean we can just take what the Australia plant is emitting and multiply that by 91.25?
Yeah, so good question. I don't think we have data at that fine a scale to easily make that calculation. One thing, so we basically, the Kolodziej plant seemed to be the only direct comparison we had, but it's still a relatively old plant. It's been in place for about 15 years now, so I was a little uncomfortable just taking the Kolodziej numbers and multiplying by 91 to come up with specific pounds released, because there are substantial differences between a pilot plant and full scale. You would be in the right order of magnitude if you did that, but you would not be any more accurate than maybe a factor of 2 or 3. So you would get close to what the scale is, but not very precise.
What would be some of those differences? Can you just elaborate on that?
Well, a lot of times if you scale something up, things tend to work better. One reason we make big plants is that they simply are usually more efficient than small plants. That's one reason why every company in the world wants as big a plant as possible. There's efficiencies that come from economies of scale. So I don't have a good feel for how much more efficient a full-scale process would be expected to be versus a small-scale process. And you could even see this in some of the environmental impacts documents that the Kolodziej plant put out. They talked about improving their process in certain ways that I think a full-scale plant would never have to do because they would have done that already. So that's kind of one of those black boxes that I had no way of estimating or figuring out.
And for the person who asked that question, did you feel like it answered it? Go ahead.
I am the person who asked that question.
So I can hear you.
I went to a presentation by Wilma Subra, and I think a lot of local people did. And the numbers there were taken from the EIS of Louisiana plant, which was supposed to produce about 1.9 million. And I used those numbers because this is a new plant and it's supposedly similar design to what they're thinking of doing here. And I come up with some really horrible numbers.
So with respect to the Louisiana plants, I do think there are some key differences in the processes that are used there. So I know we looked at the Louisiana plants as comparisons, and again, they might be correct in terms of orders of magnitude scale, but I don't think you can take the Louisiana plants and do a direct comparison to the Tacoma plant because the chemistry is different in exactly how they configured their operations and put it together. So
Are we ever going to get the information on how different?
You'd have to know how the plant is designed, and you'd have to know what feedstock it's going to use. I think those are the two kind of big ones, and if there's control technologies at the end of it. But those, I think, are questions you can ask as part of the process, right? And you can get those things specified. On the CO2 side, I think one of the Louisiana plants uses petroleum coke, maybe. Something else, not natural gas as a feedstock, which would make its emissions far greater per ton than natural gas as a feedstock. But I'm in the same boat as Ed for the CO2 stuff. I don't know. I just grabbed one emissions factor, to get the 5 million tons of CO2 estimate. And it's possible she just grabbed the same emissions factor I did, because it's the EPA one. So.
All right, and then one of the slides showed benzene as a byproduct in emissions. Any estimates for aromatic hydrocarbons? I understand that benzene is a aromatic hydrocarbon and also a known carcinogen. And again, I know you can't estimate the exact numbers, but any thoughts on that specifically?
Yeah, so I actually looked through Dr. Suber's presentation, and I didn't know where the benzene came from. I think one of the Louisiana plants that was a comparison actually they continued making methanol into things after that, so there were other pieces to the process that might explain where the benzene came from. But I saw no chemistry based in my analysis of Kugi or this that explains where the benzene can come from. And again, that's kind of the point I make with the simple molecules. To go from methane to methanol and get benzene is a pretty substantial increase in the chemical complexity of the molecule. And I don't know where that came from. I could not explain it in my own searching, and I would say I looked.
Can I ask though, if it is benzene a VOC?
Yeah, benzene's definitely a VOC.
So the Australian plant, which this would be like, doesn't list all of the VOCs. So the benzene could be one of those?
That is definitely possible. The VOCs from the Australian plant were not broken down into exactly what they were. It was just like volatile organic carbons come from the plant. They're going to be pretty simple. Benzene might be one of them, but there was no data to be able to tell that. So again, there's a lack of specificity in the data that I could find.
And it seemed like you were pretty hesitant to say that there was benzene. Is it because you think it's unlikely that the process as laid out would have the chemistry to create benzene?
I could not explain where it comes from.
Okay, so I see that there's one follow-up question. Would you like to ask your follow-up?
If I may. At a presentation 2 weeks ago that V. Godley, the president of Northwest Innovation Works, made to the commissioners at the port of Tacoma 2 weeks ago, he said that benzene would be a byproduct of the process. He said a small amount, but he said benzene was going to be there.
I would trust that information. I didn't see that.
And I see that there's one more follow-up with a gentleman with a purple shirt. Yeah. Lavender.
I was just going to suggest that.
We'll start with you, sir.
Oh, I'm Stuart. Is that identity enough? I like my anonymity. The natural gas, I believe that they'll be using in this area is about 85% purity. And natural gas does have a number of impurities, and it is possible that some of the impurities in that gas, because they're using such a large amount, could be where the benzene is coming from, since it is a shale oil derived, petroleum based. There are other chemicals within that.
Yeah, so most of those impurities in natural gas, if you look, it goes from methane, ethane, propane, butane. They're kind of the chemical sequence. I'm sure some slight percentage is more complex VOCs. And I guess if they're not scrubbed out at the beginning and they make it all the way through the oxidation processes, maybe they're there at the end. Again, that was the impurities is just the catch-all in the existing information. And so knowing specifics there would be helpful.
In your opinion, and this is for any of you, does the plant pose a danger to surrounding homes even though it is zoned properly? Sheri, why don't you go first?
I turned my mic off.
It is zoned industrial. but there are homes on the east side of 509 that are not that far away. And I don't know. That is something that needs to come out in the scoping process.
What is the airshed of this plant? Do you know off the top of your head?
Absolutely not.
Okay.
The windrows, if you look at the windrow, I have seen the windroses or the wind directions for the Kaiser stack. And that would be from the predominant wind direction was northeast to southwest with the Kaiser stack back when it was in operation. And there used to be a monitoring station, and I don't know if it still exists. There used to be a monitoring station fairly close that provided those windroses for the Kaiser stack. So due east and due west was not as predominant as northeast and southwest.
Any follow-up question to that? All right. Many of the impacts on the proposal have focused on the local area. What do any of you foresee or anticipate as far as potential environmental impacts to Mount Rainier National Park, specifically with air quality?
Well, one of the issues that I brought up earlier to these guys was the fact that methanol does produce photochemical smog. And you can see photochemical smog in Tacoma in the summer. It's that brown haze we get. And, you know, Mount Rainier would be in the direction that photochemical smog would tend to move toward the east.
All right. And in your opinion, for any of you, what is your biggest environmental concern regarding this plant?
Well, yeah, I think I said it in my talk, like spills for an accident, I think would definitely be a concern. That would have some real impacts on the bay. And I think in routine operations, I felt as I did some reading, and this is one of the things that came out when I looked at some of the Louisiana plants, venting emissions. Some of these emissions kind of in the venting and handling stage might be as important or more important than the process emissions. But again, that's a guess. I didn't have a specific number where I could compare venting versus process in terms of how methanol comes up into the air.
And with regard to the tanker regulations, both for the United States and within the state of Washington, don't regulate methanol tankers in the same way they regulate oil tankers. So all of the requirements for oil tankers don't apply to methanol tankers. They would be like a tanker, say, containing vegetable oil or any other industrial chemical. It's not handled in the same way as oil. So, for instance, you wouldn't be required to have the tug escorts that you need for oil transportation.
So I'm not sure if this qualifies as the most important or most serious impact, but it's the impact that I work on a day job, and that's if the plant is to be built, are future climate conditions being taken into account in its siting, design, and operations? So it's exposure to flood risk in the port area, its ability to reliably get power and water, and how that interacts with the anticipated future environment. And that's quite difficult when you start thinking about a facility that might be there for 50 plus years. We have a lot of the climate information to provide that informed decision. How everything else in the area changes is more difficult, and it takes coordinated effort and planning. The one I'm most curious about is the greenhouse gas question. Not one, because it is a big facility. Two, it's this kind of local versus global game that can be played in trying to understand, is this on net, having the plant here very bad for the climate? And this is a tricky question, because if you look at something like the Keystone decision, not the decision, but the environmental impact statement, the decision, in my opinion, was political and economic. But the environmental aspects of the Keystone greenhouse gas emissions were that its construction would not substantially increase greenhouse gas emissions. That's what the United States government concluded. And the rationale was that the production, the decision was not whether or not to produce oil from tar sands. It was to build a pipeline. And the assumption was that that production was going to happen regardless, production of oil. And so the emissions associated with the pipeline itself are relatively small. That is one framing for the Keystone Pipeline. Another framing is we want to keep all petro products in the ground. And so we don't approve anything that might encourage that. And so that kind of local versus global scaling is at play when you start thinking about a large petrochemical facility that is bound up in the global petrochemical cycle. And scientifically, we can come up with little estimates along the chain, but it's hard for us to do that value judgment of kind of how big you draw the box.
Joe, I have a follow-up for you. If your major concerns are about the climate impacts or implications, how well do you find that public utilities and planning agencies incorporate climate models and their impact, the projected impact of climate change on our water resources and other resources into planning for the future?
Yeah, you're really gonna try to get me fired, huh? In this region, I think we are very fortunate that start at the state level. So there is a statutory requirement that every state agency have an adaptation plan. Some are very far ahead on this, and some are just starting, but it's there. They have to be considering climate change in their future operations and their planning and their capital investment. Many of the big infrastructure folks at the regional and at the municipal level, again, are very interested. You know, Tacoma has done, although not, I don't think published, but performed a vulnerability assessment. The city of Seattle, King County, SDOT, you know, a lot of the big organizations have been looking at their vulnerabilities. Whether or not they're implementing things about that, that's a much harder, you know, we're kind of, I would say, not just in this region, but nationally and globally, just starting to get to, okay, what should we do? What makes sense? What do we do now? What do we do in 5 years? What do we do in 10 years? But I think as far as an awareness and starting to access that information and building internal capacity, we're doing pretty well, and that we have a lot to work with.
So when you say that they haven't started to implement it yet, do you mean that they have incorporated the models into their own planning models?
Sometimes. So, for example, the Northwest Power Planning Council, I think that's the right one, you know, they do future outlooks, and that includes future climate models, and they're looking at stream flows in 2050 and kind of out into the future. Now, can they always change the way that dams are operated? Not always. Sometimes they're constrained by federal and state law. There's a lot of requirements, whether they be environmental or economic, that don't give them wiggle room necessarily to just go out and start changing operations tomorrow. And that probably, by and large, is a good thing. We wouldn't want some of these big infrastructure systems to suddenly just start swinging on a dime. But I think as far as what the changes should be and where they should be, we're just starting to get to that level. Usually the time to ask these questions are when you're building something new or when you're rebuilding something that broke. And I think that's the test case is you know, are we using the information in those situations?
And then I have one more question for you, Joe, unless there's a follow-up from someone in the audience. Your slide showed some pretty dramatic increases to river flows in the area. How might this impact water access and how we manage our water resources? How might it affect aquatic species like salmon? And then, well, actually, go for that first, and then I have a follow-up to that.
Yeah, okay. So I think last year's water year is a really, really good analog for what the average year might be in 2050. In the mid-century. And the reason being, our precipitation for water year 2015 was about normal, about average, and the temperature was just 4 degrees Fahrenheit warmer. So that's kind of a middle-of-the-road guess for where we might be. What we saw, some systems actually did pretty well. Municipal water systems in big cities, not much problem. You may see some increases in rates farther down for those utilities that don't have some sort of rate stabilization fund, but in general, big cities have enough water a lot, and that has to do with where their reservoirs are and how they manage them. We didn't run out of electricity. Now, there were some changes in prices and things like that, but no one ran out of electricity in the summertime. Salmon in the Columbia did not fare so well. We had really, really substantial wildfires, not that was caused entirely by climate change, but certainly contributed by the heat. So those changes definitely are, the hydrology of the region will be very different and is already on a trajectory to be very different. And I think the key question is, can our infrastructure and our operations be malleable enough to change with them? Because, you know, based on these types of watersheds where you have snow and rain contributing, we're going to be dealing with more flood risk in the winter and the fall, and we're going to deal with more drought risk in the summer. And it's going to put, I think, management to the test.
What measures do you foresee us implementing to mitigate those impacts or adapt to it?
Yeah, I mean, the easy thing to do on the energy, the electricity and the water side is conservation. The less you use, you get away from the margin. And I think that if you look at like urban water use, for example, we've done fantastically well in the whole country in reducing the intensity of our water usage. And I think there's lots of technology to be able to do that. There's economic reasons to do that. So that's a good start. As far as what to do kind of with the other aspects of the management of the system, I think we're just going to have to be more, well, a first place to start is to look at the regulations we already have on the books. So to the extent that we have things like the Endangered Species Act, that we have requirements about how in-stream flows work and flood control work, to start to say, all right, what wiggle room do we have with those to start thinking about future conditions and not try to preserve the ecosystems and the water management systems and the energy management systems that we have now. But as far as specifics, I think that's going to have to get negotiated out kind of continuously, and there's not like a silver bullet of here's the one way we can start managing our water better.
Sheri, you mentioned the difference between cleanup standards for industrial use and other uses. Can you explain to everyone here what this means or what the effect of this is?
Well, in general, your exposure to chemicals could be higher at an industrial site than at a site that's designed for people to live, kids to play, holes to be dug in the dirt, etc. So an industrial standard for something like polyaromatic hydrocarbons is, what, 1,000 times higher than it would be for a site that would be where you would have residences. Now at the Assoc site, at the Point Ruston site, there are contained landfills and there are covenants that restrict how deep one could dig, for example, because there is contamination under caps. But in general, industrial sites have standards that allow higher levels of chemicals. The industrial sites are generally designed, the standards are generally designed so those chemicals will be contained on site and not expose either workers or move off site. So you don't want the site construction to disturb the chemicals that might remain on site. But you know, you design the industrial standards so that you can keep those chemicals in contained conditions on site.
Claudia?
Hi, Ms. Claudia. I have a question regarding standards, industrial standards. We are already housing 1,600 people in the detention center, and we just last August put another 75 people. Sure. Shall I try it again? Thank you. We are already housing about 1,600 people in a detention center not too far from the methanol plant. And just last August, we put another 75 people in the reentry center in the middle of our heavy industrial zone. So what are the protections for those people?
Well, when it comes to the Kaiser cleanup, the chemicals should stay on the Kaiser site. When it comes to the later development of some new facility on the site, that's another set of standards. That's another set of regulations that are superimposed on the cleanup levels. So, you know, we don't know what they will be yet, but we have the Clean Water Act, we have the Clean Air Act. We have RCRA, Resource Conservation Recovery Act, you know, our various laws for managing hazardous chemicals. But that new set of standards would apply with whatever facility gets built there. But you're absolutely right. It's people are housed close by, and that's not exactly what those standards are necessarily designed for.
And I'm going to just speculate that part of it was, do you think that there would be an increased risk to the people detained at the ICE detention center for chemical exposure?
We can't say that yet because we don't know what those standards, you know, exactly how the plant will be designed.
Okay, another follow-up would be if the, Ed, you had mentioned that some of the chemicals from this, if methanol spilled, it could mobilize the contamination that's already on the site. Would there be potential for it to interact with the plume of pollution from the Occidental Chemical Superfund site? And have you analyzed what that could mean?
You know, I've only been here a year and a half, so I must confess ignorance as to exactly where the Occidental chemical plume is. I think when I was thinking about the methanol co-solubilization, it really would deal with whatever was under the Kaiser site. If the Occidental plume is close or under that site, there's a possibility. So I was really thinking the pHs and possibly things like PCBs or anything else that the Kaiser site had on site. You might have a higher probability that you can more easily move those off the site and into groundwater, into the bay, if there were any kind of methanol spills or methanol seeping down through the ground.
And fortunately, there's someone who probably knows the distance in feet between the two plumes right next to you.
I don't think there's any real worry about interaction between the Kaiser site and the Occidental Chemical site. They're a long ways apart. However, if you go across Taylor Way and a little bit west, there's a U.S. gypsum site. And probably it's far enough away as well, but all I'm saying is there are other hazardous waste sites not that far away. You know, you might notice that there's kind of a little mound right at 509 and Taylor Way. And I was talking with someone at Ecology recently about what's under that mound. And that does have materials in a contained landfill that is monitored and is not leaking as far as we know, but it's right adjacent to the site. So there is another contained landfill very close. And it does have materials from OxyChem and other individuals who were kind of scofflaws in the tide flats.
Would it be fair to look into that and maybe ask for help from other chemists on this? How do the costs that we paid for Kaiser, for the land, and the costs we incurred for cleanup as a community of that site compare to the tax revenue and value of the jobs to our community that this plant would bring?
Fine question. I mean, essentially $24 million to get the site ready for redevelopment. That's significantly less than was spent getting the Assoc site ready for redevelopment. I'll say that. Very significant, quite a bit less. But again, the Assoc site was cleaned up to a higher standard than the Kaiser site.
Just check in questions because some of them overlap. This might, oh, go ahead.
I was curious. Whoa. I was curious. Never mind. Okay. So I was wondering about the local versus global game. And obviously the reason why many of us are here is because there's a very strong negative feeling in Tacoma towards the implementation of this plant. Is it possible for individuals to ensure that this plant would not happen globally either? Like through governmental.
That's a really good question, and this is the difficulty in trying to understand, what happens if we don't build it here? Does it get built somewhere else in the United States, in the Northwest, in China, someplace else? And it's really difficult. From poking around, and I'm not an expert in the methanol industry, but the few kind of trade things I found on the internet are pretty bullish. They pretty much see a lot of growth in the methanol industry because it makes plastics. And sometimes it's better to have plastics for stuff, either from durability or environmental reasons, than it is to have, let's say, unsustainable wood products or other types of things. So sometimes for environmental reasons or for cost reasons, methanol seems like a good thing, and plastics seem like a good, or the market for them is growing. I don't want to say good or bad. So from that, the chances are quite high that more methanol plants are going to get built globally. How to stop that? It's tough for an individual country sometimes to mess with an international market of that size. The long game is we'd have to stop using plastics. That's very difficult when we think about all the clothes that we're wearing, the iPhones that we have. I mean, it's all around us, right? Better living through chemistry. But it's really, you're starting to get at the heart, I think, of that 50 billion tons of CO2 is how, if we think that's a problem, or if we want to get on one of those lower emissions curves, how do we deal with the fact that we use fossil fuels and petrochemicals for lots and lots of stuff?
I think I'd actually like to make a comment about that one too, because I think I struggle with this exact issue when it comes to chemical emissions. I teach a sustainability class, and one of the topics we talk about all the time is environmental justice and social justice. And at the end of the day, you get a lot of heavy industry that emits a lot of chemicals gets cited in the communities who aren't powerful enough to complain about it, and it gets moved kind of down the chain of communities where everybody complains about it until you find a community that doesn't, and typically that's a poor community that just doesn't have the political power to say no. So I wonder, I want to discuss with my class on Tuesday, is it better to cite an industry in a place that's watching it and paying attention and maybe can improve the plant, emit less, versus kick it down the road to a community that doesn't have that power? So again, it's this global versus local game. If it needs to be built somewhere, where does it end up?
To throw in one more thing, some thinking outside the box is probably required. You can make methanol from renewable sources, and I think Joel showed a plant that does that. Now, it's smaller and probably more expensive to run than one that comes from natural gas, but it's possible. And I think that's trying to think outside the box of do it or don't, thinking what are the other technological options is really important if we care about changing which emissions pathway we're on.
Excuse me. I have a follow-up to that, actually. Is there another way to make methanol besides from fossil fuels?
Yeah.
And
I think it's waste is the feedstock. I think, is it? I'm not sure. It's the
There are a number of ways of making it from any kind of biomass.
Yeah.
We talked about that earlier. I mean, it was called wood alcohol, but it used to be made from wood. It doesn't scale; it's more expensive, et cetera, et cetera. But that doesn't mean the technology couldn't be developed.
Right.
And I think that's some of the thinking is eventually you get out of making it out of natural gas altogether. You make it from renewables.
I understand that some recent data was put out from the toxic release inventory that methanol is actually one of the top emissions in Washington state. And Sheri, can you elaborate on this?
Methanol is number 2 in terms of toxic emissions in Washington state after lead, and most of the lead is emitted from the Hanford facility. So that makes methanol number 1 other than lead. And the largest methanol emitters tend to be the process of pulping for making pulp and paper. So if you look at the list of the largest methanol emitters in the state, they tend to be pulp and paper facilities.
How does it get emitted from those facilities?
Probably fugitive emissions and up the stacks.
So I did a Google search while Ed was talking, and it said that 65 degrees Celsius is 149 degrees Fahrenheit. And that's the temperature it has to be for it to turn into gas, right?
Well, at 65 degrees, 100% of the methanol will go from liquid to gas. But just like water, even if you have water at 33 degrees, there's a little bit up in the air. So as you increase the temperature, more and more is in the vapor phase. Same thing with methanol. Even at 0 degrees, there's a little bit up in the air. And every degree you go towards 65, a little more goes up into the air above the liquid phase. So that's what the boiling point comes down to.
And in general, flue gases from industrial production are much warmer than the ambient air.
Mm-hmm. So if methanol emissions are the #1 toxic emission in Washington after lead, does that mean that there's an enormous amount of methanol sitting around the state?
Even in the port, yes, right now, today.
All right. Follow-up questions to that? Bonnie?
So what would be the effects of methanol in gaseous form and the kinds of levels we're talking about? Because the effects we've heard about from methanol are mostly if you had an enormous amount of methanol in water taking up biological oxygen demand. So what does that really mean if there's a lot of methanol in the air? I know in a lab, if you breathe in methanol, that it's toxic, but what does it mean in the open air?
Well, the actual concentration in the atmosphere would not be that high, but it is a major contributor to photochemical smog.
No, methanol is not a greenhouse gas.
All right, a couple more questions. What possible adverse environmental effects result from the tankers used to ship the methanol to Asia? Impacts could result both from pollution and the physical activities of these vessels.
I mean, I think I went over the spill case, right? Like, if you put methanol in water, it's going to soak up all the oxygen in large volumes of water. So your risk comes down to just, well, how much ended up in water? And you can just figure out, it's 1 to 198,000 if you assume volatilization is relatively minor.
So I'll focus this in a bit. I think that in an earlier version of the series, we learned that between 4 and 7 additional tankers would be in Tacoma per month. What are the other impacts of having ships in the port and shipping in and out of it?
Well, the tanker size that were listed on the Northwest Innovations webpage would be some of the larger tankers, if not the largest, coming in and out of Puget Sound.
What are some of the environmental and other risks to the sound by those tankers?
Well, we don't know who would manufacture those tankers yet. We don't know, they would assumedly be leased tankers run by someone else. So we don't know much about those tankers at all right now. So that would be something that, again, the scoping process could identify. But as I mentioned, they would not have the same regulations apply to them that oil tankers have. So, for example, oil tankers are required to have escort tugs. They wouldn't necessarily be required to have escort tugs. So that's an issue that an organization like the Pilotage Commission in the legislature could take up.
We just have a couple more questions that we have to get through before the end. So unless someone who specifically asked this question has a follow-up, please, I'll move on to the last one so we get to them. In the event of a methanol spill, either in the aquatic or terrestrial environment, how would local flora and fauna be affected by acute exposure to the methanol, not chronic? I think this is
I think that basically is the same one. Like the methanol is going to take up the oxygen in the water, and anything that requires oxygen, like fish or invertebrates or mussels, If there's not enough oxygen in the water, they're going to die. So
That's the only impact?
Direct exposure, you'd have dehydration of tissue.
Okay.
So like fish lungs, fish gills wouldn't do very well if they were exposed to a high concentration of methanol. Your
right.
lungs wouldn't do very well exposed to a high concentration of methanol.
All right.
Wouldn't it replace oxygen in the air as well, not just in the water? Why not?
In air, you have 20% oxygen. In water, you have parts per million oxygen. So you have teeny tiny bit of oxygen dissolved in water because oxygen doesn't dissolve very well in water. So in the air, unless you had a really high concentration of methanol, meaning in the percent range, you wouldn't need to worry about the oxygen factor. What you'd need to worry about is the dehydration that it causes by methanol kind of soaking water out of tissue.
And final question, this is directed at Joe, but I think that I'll just open this up for everyone. What systems or tools would you recommend the city of Tacoma have in place to truly understand the risks or impacts of this proposed project?
Well, I mean, I'll start with kind of my wheelhouse. And I think going through Tacoma's vulnerability study and then saying, okay, how does that overlap with this site is a good starting point for thinking of the climate risks on the port and on the potential plant. As far as some of the other environmental issues, and then on the greenhouse gases side, I think they need to get some specifics about the feedstock and the facility and the control technologies to really get an estimate of what they think the emissions are from the plant. Now, if the decision is they want to start looking more broadly about emissions from the transport of natural gas, emissions from the transport and use of the methanol after it leaves the area, that's another kind of policy, non-science discussion. But at the bare minimum, I think starting to get some sense of the emissions estimate, because I think that alone will be an important decision. Just, Tacoma is trying to reduce its greenhouse gas emissions, and it would be adding a potentially large source. So I think those two things would be good starting places. As far as the rest of the environmental issues, my guess is that similar kind of process details and really kind of consultant engineering studies of what they think the emissions should be are important.
Anyone else want to add to that?
I am a process person, so I'm a strong believer in the environmental impact process. And scoping has started and now stopped, but I would love to see the scoping take place and a draft environmental impact statement on the facility actually come out. Because that way we would have details that would essentially be legally binding and give us some of the data that we don't have. And there are just, in my opinion, right now, way too many unknowns. And seeing some of those in writing, some of those unknowns become knowns would be really important for me.
Yeah, I'll just echo the lack of specific technical data we have. I mean, you can't make a comparison with any accuracy without specific numbers about all the constituents, and then you'll know. How does this compare to a farm, a tanker, a set of tanks that hold petroleum hydrocarbons? How does this compare to a paper plant? How does this compare to everything else that industry is composed of? And then once you have that, you can create some figures like Joe showed us at the end of the presentation where relative risk can kind of be allocated and understood clearly. And we don't yet have that type of information.
And environmental impact statements need to include the no action option. That's one of the requirements by law. So you have everything from the full build out to various alternatives in an EIS, and that no action option is one of them.
All right, thank you, everyone. Thank you to everyone who came here and submitted questions. I didn't get to the ones that were duplicative of the fact that we can't, or get to the fact that we can't do estimates since there's not enough information. But looking ahead to next week, I hope that people will provide us feedback. We're thinking about the format because it's the last one, and we want to go over which questions the community will be which questions have been clarified through this process and that we'll be moving forward on. Obviously, the lack of information is a big problem, but feel free to email Citizens for a Healthy Bay. You can find my email or Ryan Cruz's email on our website, which is healthybay.org, and we'll be coming up with some announcements later this week or early next week. Thank you so much.